On a decibel questions number 1, it says the buzz of a mosquito produces an intensity of having a 40 decibel rating. How many times more intense is the sound of normal conversation if it has an intensity rating of 60 decibels? Okay, so you've got two things going on here. You have the sound level and you have the intensity. Now the sound level is going to be in decibels, and so we have 40 decibels, and intensity, I don't really know what to call it, so I'm just going to call it I. Now, it might be helpful to think about a 50 decibel sound level and a 60 decibel sound level. Remember, when you hear that word level, you're talking about decibels. That quantity goes by different names. Sometimes it's called intensity level, sometimes sound intensity level, sometimes decibel level, but it will always have that word level with it. Intensity, on the other hand, is just going to be called intensity and not going to have that word level. Now, here's the way these work together. Anytime you add 10 decibels onto a sound level, well, that has the effect of multiplying the intensity by 10. So I'm coupling adding on the sound level with multiplying on the intensity. So if I do it again, if I add 10 more decibels, well, then that multiplies that by 10. 10 times I would be 10I, and 10 times that would be 100I. And so I don't know what the original I was. I could figure it out, but I don't know. I don't need to for this problem. I don't know what the original I was, but 50 decibels would be 10 times it, and 60 decibels would be 100 times it. So 100. On number 2, we have a table with the right showing you the decibel level for a bunch of different sounds. They say use that bit of information to make comparisons about these intensities. All of these are compared with the top row. All of them are compared with this Smashing Pumpkins concert in the front row, which is 110 decibels. They want you to compare that to the 15th row. Now we can see that the front row is the loudest sound on the whole chart because it has the highest decibel level, obviously. And so how many times as intense is that than these other things? Well, at first you can see that the 15th row of the same concert is 10 decibels different. So I would have to add 10 decibels to go from that 15th row to that front row. And so that means that the front row is 10 decibels more, so that means it's 10 times as intense. What about the average factory? Now the average factory, you can see, is 90. And so that's a difference of 20 decibels. And so 20 is obviously 10 plus 10, and so it's going to be 10 times 10, or 10 to the second if you like. And so I might say that that is 10 times 10 times as intense. Most of us will probably just write that as 100 times as intense. Now, how about normal speech? So now normal speech is down here at 60. So again, comparing it, that's 50 decibels different. Now, you could think 10 times 10 times 10 times 10 times 10, 5 times. You could think 10 to the 5. A lot of people are going to say that that's going to be 10 to the difference in sound level, delta SL, divided by 10. Think about that. That would have worked for A and B, and now it's going to work for C. So here's what I'm saying. If I'm adding 10 decibels 5 times to get 50, then I'm going to multiply by 10 5 times, or multiply by 5 tens. And so it's going to be 10 to the 50 over 10. That is 10 to the 5. And so it's 10 to the 5 times as intense. The library at school, now the library at school they have as a 40 to 110, so that's going to be 70 decibel difference, or 10 to the 7th times as intense. And the sound which most humans can barely hear, which is our threshold of hearing, that's going to be 110 decibel difference And so that's going to be 10 to the 11th times as intense. See where I got that from? I took that 110 divided by 10. I got 11 times. That's 11 times you add 10 decibels. 11 times you multiply by 10. So 10 to the 11th times as intense. Huge number. On number 3, it says, on a good night, the front row of a Twisted Sister concert would surely result in a 120 decibel sound level. A Walkman produces 100 decibels. How many Walkmen would be needed to produce the same intensity as the front row of the Twisted Sister concert? Now, here's what you got to understand. Sound sources, Walkman or a concert, they would contribute equally to the intensity, but not equally to the intensity level. So that says that if I have 2 Walkmen, that doesn't mean that it's 200 decibels. No, because in fact, 200 decibels is louder than the loudest possible sound in air. So think about this. If I'm comparing 100 decibels to 120 decibels, we saw from those last examples that that is 20 decibels difference. So I added 20 decibels. So that means that's 10 times 10, or 100 times as intense. And there's our answer, because the 100 times as intense means to get something that's 100 times as intense, you need 100 of those things. And so if one Walkman would give you the intensity of 100, so this is one Walkman, so then if I need something that's 100 times as intense, I need 100 of those Walkmen, because I need 100 times as much energy in the air. And so for this 120, this intensity would be 100 times as intense, and so that would mean I'd need 100 of those Walkmen to make that sound. On number 40, it says if the power of a sound source doubles, the intensity level at a certain distance from the source increases, exactly doubles, or decreases. Well, we can see something here. We can see that the intensity is the power divided by the area. Now, if the power increases, so it goes to something bigger for the same distance from the source, so that means the area, the cross-sectional area of the circle is going to be the same, then this obviously is going to be a bigger I. I should get that equals out of there because it's not equal. This is going to be bigger. In fact, you can see if this P is twice as big as that one, then this I is going to be twice as big as what I started with. I'm just calling it I naught here. And so if the intensity is bigger, then that means the intensity level associated with it is bigger too. They're not linearly proportional, but they are proportional in that if I have a smaller I, then I'm going to have a smaller amount of decibels, and if I have a bigger I, I'm going to have a bigger amount of decibels. Now, the second part of this is actually pretty neat and maybe a little bit counterintuitive. It says, what are the intensity levels at a distance of 10 meters from a 5 and a 10 watt source? So if I'm going to figure this out, first I'm going to figure out the intensity. And so let's do the 5 watt source first. Let's say that the intensity from the 5 watt source is going to be the power of that divided by the area. That's the power of it divided by, if you assume that it spreads out uniformly in all directions, which isn't always the case, but it will always be for us, 4 pi r squared will be that surface area of the sphere. Okay, so now the power is 5 watts, and the 4 pi r squared, we're 10 meters away from the source, so 10 meters squared like this. And if you run that through your machine, you get a number that looks pretty small, 0.00398 watts per square meter. First thing you want to ask yourself, is that loud or not loud? And we'll see that in a second. And then they say, what about a 10 watt? Well, with 10 watt, it's not hard to see that now this numerator is going to be twice as big. And so this answer is going to be twice as big, 0.00796. watts per square meter. So now we're going to take those and we're going to figure out the corresponding sound intensity levels for them. So for the first one, we're going to say that the sound intensity level 5 meters away, well, that's 10 decibels log base 10 of I over I naught. That's, you're taking the logarithm of that entire quotient. And so it's going to be 10 decibels log base 10 of this number divided by the threshold of hearing, since we're not comparing it to something else. 1 times 10 to the minus 12 watts per square meter. If you go ahead and run that through your machine, you're going to get a 96 decibel sound level. And you're a little bit more familiar with that. And you know that that's not mega loud, but that's not mega soft either. And so, yeah, I would say that this, even though this intensity looks pretty small, it's pretty decently loud sound. Now, here's the thing that might be counterintuitive to you. If I'm going to put twice as much intensity in that numerator for the red one, then are you going to get twice as many decibels? Well, no, because that's not the way logarithms work. In fact, you're going to take this red one, you're going to put it in the numerator, and true, this quotient is going to be twice as big as it was before. But ironically, it only gives you 99 decibels. And that's a good thing to remember, that whenever you double the power, you're going to just simply add 3 decibels onto it. And you might say, well, it was 3 decibels this time. Is it going to be, it won't be 3 decibels other times. Yes, it will. And I don't care if you start with the soft sound and you do twice as intense as that, or if you start with a super loud sound and do twice as intense as that. The louder sound is always going to be 3 decibels higher than the softer sound. And so that's what you're going to see. Well, number 41, it says the intensity levels of 2 people holding a conversation are 60 decibels and 70 decibels respectively. What's the intensity of the combined sounds? Maybe it's not a conversation anymore if they're talking at the same time, but what kind of intensity are you going to get of the combined sounds? And they didn't ask, but I'll ask, how many decibels if they talk at the same time? So what I'd like to do here is figure out the intensities that each one is contributing to the air, and now add those together. That'll actually be the answer the way it's written, and then I can take that intensity and figure out the associated sound level. And that's a part that might make you a little bit, oh, I didn't see that coming. So check it out. What is the intensity of someone talking at 60 decibels? How much energy are they putting out into the air? What kind of intensity do we have there? Okay, so some people might be able to go, well, hey, I know that 0 is 1 times 10 to the minus 12, and then just step up a few times. But that only works because it's a multiple of 10. So let me show you how I would do it. I would say that the difference in sound level is 10 decibels times log base 10 of I over I naught. Now, the change in sound level is 60 decibels here, and that's equal to 10 log base 10 of I over. Now, when you used to say 60 like that, of course, you're comparing to the threshold of hearing. So I'm going to put 1 times 10 to the minus 12 in that denominator, and that is in watts per square meter. Now, I want to try to solve for this intensity. And you know that involves going from exponential notation to logarithmic notation or back. So what I'm going to do is I'm going to first divide off the 10 decibels both sides, and I'm going to get 6 on this side. And the decibels are going to cancel out as well. So I have 6, and that's equal to log base 10. I know a lot of people don't write that 10 down there. They know it's understood, but I'm writing it there for emphasis. I got to tell you, sometimes people forget what to do until they remember that there's 10 down there. Now, I'm going from logarithmic notation in this line to exponential notation in the next line. And remember, this is the base. This is the exponent. Logarithms are exponents. And then this is the answer. So I'm going to write something that looks different. 10 to the 6 equals I over 1 times 10 to the minus 12 watts per square meter. Now let me multiply both sides of this by 10 to the minus 12 watts per square meter. 10 to the 6 times 1 times 10 to the minus 12 watts per square meter. Well, really, you're looking at 10 to the 6 and 10 to the minus 12. Same bases, different exponents, just add those exponents together. And so I'm going to have 10 to the minus 6 watts per square meter. That's for that first person. Now for the 70 decibel person, I'm going to just simply put a 70 right here. And that's going to bring me down to this line. It's going to be exactly the same. 7 equals log base 10 I over 1 times 10 to the minus 12 watts per square meter. And so you see I'm going to write into exponential notation 10 to the 7th equals the fraction. And then I'll cross multiply, and I'll end up with 10 to the 7th times 10 to the minus 12, 10 to the minus 5 watts per square meter for this higher intensity. Now this question is just about done. This question said, well, what's the intensity of the two of them together? You couldn't just add their decibels together, but you can just add their intensities together. So now you might say, well, I need my calculator for that. You don't really need your calculator for this. This is 1 times 10 to the minus 6, aka 0.1. I'll make that look 10 times smaller, so I'll make this part look 10 times bigger, and now that's not bad to do in your head. So I have 1 times 10 to the minus 5 and 0.1 times 10 to the minus 5, and I'm just going to add those two things together, and it's going to be 1.1 times 10 to the minus 5 watts per square meter, and that's that combined intensity that they were talking about. Now I asked a follow-up, how many decibels would that be? Now at first, somebody doesn't understand this very well. I say I have a person that's speaking at 60 decibels and simultaneously a person speaking at 70 decibels. How many decibels? You know enough by now to know that it's not 130, but you know there's a lot of people out there that would say that. Calculating it's pretty easy. I'll just say that the change in sound level is 10 decibels, log base 10 of I over I naught. This is going to be the numerator. The threshold of hearing is going to be the denominator, 1 times 10 to the minus 12 watts per square meter. And you might be surprised, but you end up getting a decibel level of 70.4 decibels. Of course, it was more than 70, but it wasn't 130, and it wasn't even 3 more than it. It was only a little bit more. On number 42, it says a person has a hearing loss of 30 decibels for a particular frequency. What's the sound intensity that is heard, that's going to be for this person, at this frequency that has an intensity of the threshold of pain? Now, this is something that you may have had to look up. The threshold of pain and is going to vary from person to person, but just like the threshold of hearing is taken as that 1 times 10 to the minus 12 watts per square meter, threshold of pain is going to have a value that we're going to use as an average too. We'll generally say that the threshold of pain is 1 times 10 to the 0 watts per square meter, so not times 10 anything. Now, if you would go ahead and run that through the sound level equation, you would see that that corresponds to 120 decibels. Now, does everybody describe 120 decibels as painful? No, some people are going to describe it, a softer sound as painful, or some people are going to say, no, 120 decibels doesn't bother me, but this is an average that we use. So now, this person has 30 decibels of hearing loss, and so what that means is there's something going on with their ear so that 30 decibels worth of energy, I didn't say 30 decibels of energy, but 30 decibels worth of energy is somehow being dissipated. Whether that's because their eardrum is harder than it should be, there's something's wrong. And so the sounds are dropped by 30 decibels. So all that is to say, when we hear this sound, and the average person is getting 120 decibels and 1 watt per square meter, this person, well, they're hearing 120 minus 30, or only 90 decibels of intensity level. So they want to know what is that sound intensity that's actually getting into their eardrum. Well, easy enough. I can say that change in sound level is 10 decibels log base 10 of I over I naught. And so I'll put my 90 decibels here. I'll put my 10 decibels there. Log base 10. The answer over the threshold of hearing. So I'll divide both sides by the 10 decibels. I'll get 9. I'll take both sides raised to the power of, or I'll rewrite this so that it says 10 to the 9 is equal to I over 1 times 10 to the minus 12. If you didn't follow that math step right there, just check the last example on this same video, and I go through that a little bit slower. And so you can see then that this intensity is going to be 10 to the 9 times 10 to the minus 12, or 10 to the minus 3 watts per square meter. We might often write that as 0.001, but maybe I would write that as 1/1000th watts per square meter. And so all that is to say, this person is losing 1,000 times the energy to some mechanism in their ear. Number 43, they gave this chart of different aircrafts, and they asked what are the highest and lowest intensities for takeoff and landing for these aircrafts. So really this is a practice round, 4 practice rounds of converting from decibels to intensities. And so a lot of us would be tempted to just pick out the numbers, and we certainly do have to pick out the numbers. I'm looking at this takeoff column, and I see that this is my lowest intensity level for takeoff, and here's my highest intensity for takeoff. And then for landing, I see that my lowest is this 99.8, and my highest is this 107.8. And you could just go ahead and plug those numbers in if you really wanted to do that. But watch this. Let's say we know we have the equation that the change in sound level is 10 decibels log base 10 I over I naught. What if I just rewrite that without putting anything in? So I would have that change in sound level over 10. I'm going to leave the decimal part off. Is equal to log base 10 I over I naught. And now I'll write this in exponential notation, and I'll go 10 to the change in sound level over 10 equals I over I naught. And so I'm going to take, and I naught is going to be the same on all of these, and so it's going to be I naught times 10 to the change in sound level over 10 is equal to the intensity. So once I get to there, now all I have to do is 4 times. Let's take 10 to the minus 12 times 10 to the what? 85.7 divided by 10, 8.57 equals that intensity. And you could just add those two things together and get a 10 to the, what would that be? 3.43, negative 3.43 watts per square meter. If you do want to, you can put that in the machine. I did that before I made the video. 3.72 times 10 to the minus 4 watts per square meter. And you could just keep going with that. You could put in here 10 to the 11 times 10 to the minus 12. You can see that that one comes out pretty nice. That'll be just 10 to the minus 1 watt per square meter. And then you could do the same thing again with the 99.8 and the 107. If you go ahead with those, you end up getting 9.55 times 10 to the minus 3 watts per square meter and 6.03 times 10 to the minus 2 watts per square meter. And on number 45, they say a compact speaker puts out 100 watts of sound power. Neglecting air losses, at what distance would the sound intensity be at the threshold of pain? I gave you the threshold of pain down here as a hint too. And then in part B, it says neglecting air losses, at what distance would the sound intensity be that of normal speech? And they want you to justify your answer and see if your answer makes any sense. 100 watt sound of power is like a regular speaker. A speaker in your car would probably be about 100 watts. So this isn't something super small, but this also is not something that's like for a concert or anything like that. Very, very ordinary run-of-the-mill speaker. And so that speaker is going to be right here, say, and they want to know where is this spot so that that's the threshold of pain. It has that intensity of 1 watt per square meter. And then, of course, the normal speech is going to be lesser than that. Most of the time, you take normal speech to be 60 or 70 decibels. We're going to go 60 decibels here. I know that's what our authors wanted here. And so there's another spot out here, and don't judge the relative distance based on my sketch here, but this intensity is going to be whatever goes along with 60 decibels. Now, we went through a couple of examples that let you convert from intensity levels to intensities, and so I hope at this point you're able to go to 10 to the minus 6, maybe not necessarily just in your head like that, but I hope you know the technique, and if not, just look at those last couple of examples. So this intensity is going to be 10 to the minus 6 watts per square meter, and we want to know what these two distances are. Okay, so remember that intensity is power divided by area, or if the power is going to spread out uniformly all over, that area is the surface area of a sphere, and it's 4 pi r squared. So now let me solve for r, and I'll say that it is the square root of the power divided by 4 and pi and the intensity. And so all I really have to do now is plug those in. I have 100 watts in the numerator, 4 pi, and the first time I have a 1 in the denominator, which is kind of nice, watts per square meter. You can see this comes out to 2.82 meters away. The second time, that's going to be R1. Now for R2, I'm going to put in a 10 to the minus 6 up here, and so this is going to come out to just some powers of 10 off, but a million powers of 10 off. This is going to be 2820 meters, and that's going to be, you know, quite a bit, pretty far. These are our two distances, but this is assuming that we have no losses based on the air. They asked, does your answer seem reasonable? Do you realize we're looking at a number here that's like 1 3/4 miles, and we're from a 1 3/4 miles away from a normal speaker? Are we getting something that just, you know, sounds like normal conversation, kind of like I'm talking to you now? It doesn't seem realistic. It seems like that the air is going to absorb a lot of that sound, and so these would be very, very idealized cases. On number 52, we have an office and e-commerce company, and they have 50 computers. And those computers together have a sound intensity level of 40 decibels, which isn't very high. But the office manager wants to cut the noise in half. And so the office manager wants to go from 40 decibels down to 20 decibels. I don't know why you'd want to do this, but okay, that's what the problem says. And he takes away half of the computers. Does he achieve his goal? Now, you know what happens whenever you take the intensity and cut it in half. You know what that does to the sound intensity level. This guy doesn't know it, so let's sort of pretend like we don't know it either, and let's see what happens. So here's the thing. The computers do not contribute equally to the 40 decibels. They contribute equally to the intensity, but not to the intensity level. So what I want to do is I want to see how much intensity are we talking about total with 40 decibels, and then we'll divide that over the 50 computers. We'll see how much each one is contributing, and then we'll take away half of them, and then we'll see what decibel level that gives you in the end. Okay, so that's the plan. So here we go. We know that change in sound level is going to be 10 decibels log base 10 I over I naught. And so I'm going to say 40 decibels is 10 decibels log base 10 of I, that's what I'm looking for, over to 10 to the minus 12 watts per square meter. I'll divide both sides by the 10 decibels and I'll get 4 equals this log base 10 I over 10 to the minus 12. And maybe by now you're starting to get bored of that same thing, and that would be good because that means you know what you're doing. 10 to the 4th equals I over 10 to the minus 12. And so now you can see that the intensity is 10 to the minus 8. You may have even just counted up from the threshold of hearing and got that, which would be okay too, especially because it's a multiple of 10. Okay, so now that's the intensity of 50 computers. So if I divided that to get the intensity of one computer, it's that 10 to the minus 8 watts per square meter over 50. And we would get, well, that 50 is the same as 5 times 10. And so it's a fifth, or 0.2 times 10 to the minus 9. You might not like that. You might want to just go to your machine, and that's okay too. So that's the intensity of one of them. Now, remember, he takes 25 of them away, and so he's left with 25 of them. And so that says that the intensity of 25 of them is 25 times the intensity of one of them. And so 25 times 0.2, that's a fifth of 0.2, that's 5 times 10 to the minus 9 watts per square meter. And again, feel free to do that on your machine if you would like. Now, what did he achieve his goal? Did he go down to 20 decibels? Well, let's see. Change in sound level is 10 log base 10 I over I naught. I'm going to take that 5 times 10 to the minus 12 watts per square meter, put it in the numerator. I'm going to put my threshold of hearing, 1 times 10 to the minus 12 watts per square meter. Run the calculation through, and you see that no, he doesn't. He actually got 37 decibels. Now, who saw that coming? I think I saw that coming, because we started with 40, we went down to half the intensity, and anytime you either half or double the intensity, you're talking about reducing or increasing by 3 decibels. And so this person is probably going to be very surprised. How could half of the machines only give a 3 decibel difference? Well, that's because it's logarithmic, in short. In fact, if he wants to get down to 20 decibels, he's going to have a very difficult time to do that, because if you think about, well, how many computers versus the amount of decibels he has, 50 computers gave him 40 decibels. So then 25 computers would give him 37 decibels, and 12 and a half, I don't know how you get that half, but 12 and a half computers would give 33 decibels, not 34 decibels, and then 6.25 computers gives 31 decibels. And you can see this is going to be really difficult to get down to 20. 3 and an eighth gives the 28 decibels. 1.5 and a 16th, 1 and 9/16 gives the 25 decibels. He has to have, you can see he has to have less than one computer just to get down to 21 decibels. And remember, it was an e-commerce company, so I think computers are kind of important there. The whole point is, anytime you reduce the intensity by 2, factor of 2, you take away 3 decibels.